Hello, hello, hello. Hopefully everybody's doing good out there. If you have not already looked at part 1 on dividing and rationalizing denominators and done some practice questions, you need to make sure you do that first. You got to have a good grasp on the easier stuff before we take a harder look at the harder stuff, which is in this video. So just a quick review here of what we looked at in that previous video. Talked about dividing radicals, and then we looked at this process called rationalizing the denominator. And so rationalizing the denominator, what we do is we want to get rid of the irrational or the radical number on the denominator. And to do that, we times by whatever that radical may be. So when I do that, I take it to the numerator and to the denominator because then I'm preserving equality. The reason for doing that is when I times, root 5 by root 5, I get the square root of 25, which is a rational number of 5. Today, what we're going to look at is something similar, except for now, rather than have a monomial on the denominator, we have a binomial, okay? And so we have two terms on the bottom. So rationalizing binomial radicals involves the same method as we used previously, except for now we have to use the difference of squares concept to get rid of the radical, which is also called a conjugate. So for example, a plus b, the conjugate to a plus b is a minus b. And so just to review of what difference of squares is, right? If I factor x squared minus 100, I would get x minus 10, x plus 10, right? These are conjugate factors. One's positive and one's negative. And the nice part about doing that is when I'm multiplying with difference of squares, I really only have to multiply out the first and the last term. The inside terms there end up canceling each other out. So let's take a look at this just in this kind of practice example to show why we use difference of squares, and then we'll go actually look at rationalizing and simplifying from there. So to rationalize the denominator in this, I have this binomial. And so to rationalize, I need to multiply by the conjugate term. So the conjugate term to 6 plus root 7 is 6 minus root 7. And what I multiply by the denominator, I'd also have to do to the numerator. Now, for the sake of this question, I'm just ignoring the numerator, and I just want to talk about what happens on the denominator and why it's important. I already kind of outlined it, but let's just summarize. So if I multiply these two binomials out completely or FOIL them out completely, right? I take the first terms and I multiply them, I get 36. I take the outside terms and I multiply them, I would get negative 6 root 7. I take the inside terms and I multiply them, I would get a plus 6 root 7. And I take the last terms and I multiply them, and I would get minus the square root of 49. So when I have FOILed this out, right, first outside, inside, last, or multiplied out altogether, these two middle terms are opposite, and they end up canceling each other out. So when you're multiplying by a difference of squares, or when you're multiplying by a conjugate, we don't actually have to complete my full FOIL because that's going to happen every time. The two middle terms are going to be identical and cancel each other out. So all I need to multiply here are the first terms together and the last terms together, just as a shortcut. So when I simplify this, right, this would be 36 minus the square root of 49, which is just 7, would give me 29. And so that would be my new rationalized denominator. And as long as I don't have a root sign in the denominator, I know that I'm kind of on the right track. Okay, so that's why we use that difference of squares concept to help us rationalize binomial denominators. So let's go look at how that works in a few examples, and then what we need to do to simplify from there. So A is the same thing, so rationalize the following denominators. So I need to take this and multiply by the binomial conjugate. So the conjugate of 4 plus root 6 is 4 minus root 6 and 4 minus root 6. So I'm going to multiply this and multiply this. So on the top, this monomial needs to get multiplied in to both of the terms in that binomial. So 5 root 3 times 4 would give me 20 root 3 And 5 root 3 times negative 6 is going to give me a negative 5 root 18. On the bottom, well, I have conjugate terms, and I don't want to multiply out, FOIL out those binomials every single time. So you gotta, or if you don't remember the rule, it's fine. You can do that, but ideally we remember the rule. So all I need to do is multiply out the first and the last terms. Because these are conjugate terms, I don't need to do the middle two terms of FOIL. So 4 times 4 is 16. And the root 6 times negative root 6 is going to be a negative 36. So from here, I just want to simplify as much as possible. So looking at this first term here, 20 root 3, I can't simplify that term anymore because root 3 is as low of an irrational number as I can get. The next one is negative 5 times 18. Well, I know that 9 is a perfect square and the index is 2, so I could break this up into 9 and 2. And the square root of 9 is 3. So when I write that out, this term I said stays the same. Sorry. Minus 5 times 3 root 2 all over the 16 would stay the same, minus the square root of 36, which is a nice whole number of 6. So I will try to continue simplifying here. Again, I said I can't touch this one, 20 root 3. This would just get multiplied together, so minus 15 root 2 over 10. So I know I've successfully rationalized the denominator because I'm just left with a rational number on the bottom. I don't have a radical. And I can't simplify my numerator any further because these are not considered like radicals. Now, I always want to go, if I can and I have time and I know how to type it in on my calculator, I want to check because that's a little bit of work. It looks a little bit messy. Let's go check that I did all of that correctly. Part of the problem is sometimes it's hard to put this in on your calculator. So make sure you put brackets around your numerator and denominator. So we started off with 5 square root of 3. Is being divided by 4 plus the square root of 6. Okay, so that's the first decimal. Let's see if that equals our answer. So our answer, once we rationalize the denominator, I'm just going to put brackets around my term. So 20 square root of 3. So bracket around the term. And bracket around the numerator. So 20 root 3 minus, 15 square root 3. Oops, I should put a bracket around these terms just to make sure. Oops. Second. Insert bracket. Thank you. Okay, so then I close the bracket around the term, close the bracket around the numerator, and then I'm going to divide that by 10. And I should get the same decimal, but I didn't, so I did something wrong. Oh, I see what I did wrong. I put a root 3 here rather than a root 2. So looking at this line and this line, I had the same decimal, so I know that I have typed that in on my calculator correctly or that I've rationalized correctly. Again, the problem becomes making sure you put all those like really ugly radical numbers on your calculator correctly. Okay, well, let's go look at another example. Which one do I want to do here? I'm gonna do I'm gonna do B part 1 because again, I'm terrible with the alphabet, and then you'll do this one on your own. So I'm gonna take a look at this one because it's a little bit more difficult. So my process is the same. They're saying, rationalize this denominator. So I have to multiply by the conjugate term. Now, before we could kind of ignore the coefficient, I'm not going to ignore the coefficient now. I could take out a GCF and do all that work, but I'm not going to worry about that. Let's just take this whole thing and multiply it by the conjugate term of the denominator. So the conjugate term of 4 root 5 minus 2 is 4 root 5 plus 2. So whatever I multiply the denominator by, I also need to do that to the numerator. And so on the top here, what's happening is this is going to get multiplied to both of these terms. So 3 times root 10, 3 root 10 times 4 root 5. So 3 times 4 is 12. And 10 times 5 is root 50. Plus 2 times 3 root 10. So plus 6 root 10 over the denominator. Now, because I multiplied by the conjugate, we can remember that if we're foiling this out, we only need to multiply the first term and the last term together. So 4 root 5 times 4 root 5 is going to give me 16, the square root 25. And negative 2 times a positive 2 is going to give me a negative 4. So now I'm going to simplify this as much as possible and just kind of take it one term at a time to simplify. So 12 times the square root of 50. Well, I know 50 can be broken into two perfect squares of 25 and 2. So I would say that that is 12 times 5 root 2 plus 6 root 10. Root 10 can't be broken into any perfect square, so I just leave that as 6 root 10. Next one would be 16 times the square root of 25. Well, I know the square root of 25 is actually 5, so really this is 16 times 5, which gives me 80 minus 4. So just to simplify again, I'd end up with 12 times 5, which is 60 root 2 plus 6 root 10 all over 76. Okay. You could say that's your final answer. The problem is most of the time that is not going to be considered your final most simplified form. And this kind of comes back to what we looked at when we did quadratic function is, you get to this form when you use quadratic function, but that wouldn't match up with one of the answers, A, B, C, or D. And the reason for that is because you still need to go look at all of your coefficients. So 60, 6, and 76. Could they all be divided by a common number that would kind of, simplify that fraction or that radical as much as possible? So 60, 6, and 76, I know could all be divided by 2. Okay? Because I'm dividing all of the terms by 2, it doesn't change equality. I preserved it still. So 60 divided by 2 is 30 root 2. I can't do that to my radical functions because they're inside. They're not the coefficient. They're the radical. Plus 6 divided by 2 is 3 root 10. And 76 divided by 2 is 38. Those cannot be simplified any further, right? I can't divide a 2 or a 3 out of any of them. So that would actually be the final answer that would appear on the test. Okay. I would like you to take a second and pause the video and try B on your own. And then check your answer in a second. So hopefully you pause the video, try that on your own. We're going to take this and multiply by the square root of 5 plus 7 over the square root of 5 plus 7. That's the conjugate of my binomial radical denominator. And I want to preserve equality, so I do it to the top and bottom. So then I will multiply 11 to both of these terms. So 11 times root 5 is 11 root 5, and 11 times 7 is 77. This here, I have two binomials that are conjugates being multiplied out. So I only need to multiply the first term. So root 5 times root 5, well, that's the square root of 25. So that's 5. I really just get rid of the radical sign there. And negative 7 times a positive 7 is a negative 49. Then I want to go simplify here as much as possible. Well, 11 root 5, I can't simplify that at all. I also can't add these together because they're not like terms. So my numerator would stay as 11 root 5 plus 77 over my denominator when I simplify this. So 5 minus 49 is going to give me a negative 44. So there's my answer. I can always put that on my calculator. Put this on my calculator. You should get about 2.30, and that on my calculator, I should get the same kind of irrational decimal. C is already done for you in the node package. I'm not going to go through that. The process ends up being the same. It's just a little bit more multiplication because the numerator is a binomial in that example. So check the homework if you're curious, or sorry, the note package if you're curious. This part is rationalizing denominators when we have a variable as part of my denominator in the radical. So the questions over here were strictly numerical examples. Now we're going to look at questions that have variables in the denominator. Process is going to be exactly the same, except for now we have this other part that says state any restrictions. So I'm just going to go solve, and then I'll talk about what that state any restrictions here means in a second. So 5 over the square root of 6x. So if they want me to rationalize this denominator, my process is the same. I times this by the square root of 6x times the numerator by the square root of 6x. So 5 times root 6x is just 5 root 6x. And root 6x times root 6x is 36x squared, which I'd square root. And I just end up getting rid of that radical sign. Okay, so there's my answer once I have rationalized the denominator. The problem becomes I need to do this other part, which says state any restrictions. So just kind of an extension here for you guys is when I take a look at a radical function, let's say I graph the square root of x. Well, the square root of x, and I really only need this first quadrant, so that's all I'm going to draw. 2, 4, 6, 8. Let's go. Okay. The function of the square root of x, if I sketch this out, well, what's the square root of 1? 1. What's the square root of 2? Well, root 2, ugly number, right? What's the square root of 4? It's 2. What's the square root of, let's say, 9 is right here? Well, it's 3. And so square root functions look like this. And they stop right here at 0, 0. Because I can't put in any of those numbers, right? What's the square root of negative 10? It's a non-real number. So the reason we have to have some restrictions on my domain or on the values of x's is because depending on the graph or the location of the graph, there's always going to be numbers that x value cannot equal. In a basic radical graph or the square root of x, you couldn't be anything less than 0. Here, the thing to remember is we can now put transformation. So I could move this function anywhere, and that would change the restrictions on the domain. And so what we need to do is use my denominator to help me figure out exactly where that restriction would be. So to find the restrictions, what you're going to do is you're just going to take the denominator. So solve for the denominator. Where is the denominator greater than 0, right? We need the denominator to be greater, or the x value to be greater than 0, because we can't have a negative number underneath that root sign. I also can't have a 0 on my denominator because I can't divide by 0. So when I'm doing this, I'll take my original denominator of 6x. Where is 6x greater than 0? And I can do this kind of like 2 ways. It doesn't really matter how I do it. So I'll take, where is the square root of 6x greater than 0? Well, to solve for x, I need to square this, which doesn't do anything. It just gets rid of that 6x, or the square root. So now I'm left with, where is 6x greater than 0? Well, x needs to be greater than 0. That's the restriction on my domain. And so I just need to put it there accordingly. I'm going to ignore C. It's a little bit complicated. If you're curious and you want to try it by yourself, go check my answers that are in my answer booklet for the note pack online. I'm going to go through B, though. So B works the same way. So I have 10 over the square root of 3x minus 2. First thing they want me to do is rationalize the denominator. So I'm going to do that by multiplying by a conjugate term, because this is a binomial. So I'll go 3x plus 2 and times by 3x plus 2. So I need to multiply this 10 to both of these terms. So 10 times the square root of 3x, so 10 root 3x. And 10 times 2 is just plus 20. Over, now I multiply these binomials out together, and because they're conjugates, I only need to multiply the first and last term together. So root 3x times root 3x is just going to give me 3x once I've simplified. And negative 2 times 2 gives me a negative 4. Looking at that function, I actually can't simplify it any further. So 10 square root 3x simplified. 20 can't add that. They're not like terms. Can't divide anything by a common factor. So that's going to be my final answer. Now what I need to do is say, well, where is that denominator greater than 0? And I can use this denominator or this denominator. It's not actually going to change. So where is my denominator greater than 0? So where is the square root of 3x minus 2 greater than 0? Where is that happening? So I'd have to add 2. And then I have the square root of 3x needs to be greater than 2. So I would square this and square this. So I have 3x is greater than 2 squared is 4, and divide that by 3. So in order to have a function that works and not be, in the unknown area over here, the restriction on the domain is that x would have to be greater than 4/3, which is saying, like, if I chose to substitute a number like -1 into here, I'm not going to get an answer. Even if I substitute 1 into here, I'm not going to get an answer that would work or be a real number. Okay. So that is rationalizing the denominator, the harder portion of it. If you want to go take a look at the rest of your homework there, I had already told you kind of to try A to K previously, so go take a look and attempt, at least 4 or 5 of the remaining questions in number 1, and make sure you try numbers 1 and 2. Okay, and there will be a quiz to follow that you'll have to complete. Any questions, please fire me an email or comment them below if it's just a quick question I can clarify for you. Thank you.